5.2 Perpendicular and Angle Bisectors. In this lesson, we are going to talk about perpendicular bisectors. We are fairly familiar with those. Remember, perpendicular and bisect are two separate things. And angle bisectors. What we're going to look at here is, in our diagram here, segment CD, line CD, is perpendicular to and bisects segment AB. Okay, so it is perpendicular, that means right angle, and it bisects, right? Perpendicular means right angle. Bisect means two congruent segments here. CD is perpendicular at the midpoint, right? Midpoint, definition of midpoints, two congruent segments. And what we are going to do is choose a point on the perpendicular bisector. And what are we going to do with that? Well, we're going to draw our triangle over here. So we connect this point with the endpoints of our segment, and we make two triangles out of it. Now you should look at this and go, oh, hey, we've got side angle side. Those are congruent. Now we can start making all the parts congruent. So we could make these angles congruent. We could make these sides congruent. We could make the top angles congruent. Right? Everybody's going to be congruent. The parts that we are interested in, and if you notice, we have an isosceles triangle here. And do you remember our awesome theorem said that if you have an isosceles triangle and you bisect the vertex angle, that it is the perpendicular bisector of the base? This is very similar to that. But the two pieces that we are interested in are the two legs of our triangle. So because these two pieces, these two segments, segment CA and CB, are congruent, we can say that their lengths are the same, which means we can say that point C is equidistant, right? What does equidistant mean? Equal distance, equal length, is equidistant from our points A and B. C is equidistant from points A and B. And what this is going to do for us is our perpendicular bisector theorem. So let's take a look at this. The perpendicular bisector theorem, I bet we're going to have a perpendicular bisector, says that any point on the perpendicular bisector of a segment, okay, so let's look over here. We have a line that is both perpendicular and bisects this segment. That's important that it's a segment. So we are given perpendicular and we are given bisect. This is bisect right here. Our lengths are equal. We could also, if we were told that they were congruent, right? We could also have segment MA is congruent to segment MB. Our lengths are equal, which means they are congruent. This tells us bisect. If it's marked, it tells us bisect. So we have a perpendicular bisector of a segment. And what we are going to do is choose a point on the line that is the perpendicular bisector. So let's go back to our requirement. If a point is on the perpendicular bisector of a segment, so we have a point that is on the line that is the perpendicular bisector of the segment, then the point is equidistant from the endpoints of the segment. So this is congruent to this. We could also say that segment PA is congruent to segment PB. This is definition of congruence, right? Equal length means congruent segments. So this is a really cool thing. If you have a perpendicular bisector, any point on that perpendicular bisector is equidistant from the endpoints of the segment. All right, and we have the converse of the perpendicular bisector theorem, which is going to say what? It says that if a point is equidistant from the endpoints of a segment, so we have our point, and it is equidistant, right, because PA is congruent, segment PA is congruent to segment PB. That means it has equal lengths, definition of congruence. So if our point is equidistant, then the point is on the perpendicular bisector of the segment. So we can draw a line through point P and the segment, and it will be perpendicular and bisect the segment. Right? We can say that it is perpendicular and it bisects. Segment MA is congruent to segment MB. Again, definition of congruence here. Well, what does this do for us? We can use it to do algebra. What is the length of segment AB? Well, we look at our problem here and we say, hey, we have a perpendicular bisector. You see that? Segment BD is a perpendicular bisector. So I know that if I choose a point on the perpendicular bisector, any point on that line, then it is going to be equidistant from the endpoints of the segment. And if it's equidistant, then they are congruent, right? So I can write the length of BA equals the length of BC, substitute in, we get x equals 5. Then we can put our 5 back in, and we do 4 times 5, and we get 20 units. And 6 times 5 is 30 minus 10 is 20 units. And we should not be surprised that they are exactly the same. Okay, go ahead and pause the video, and you try the next problem. That was fun. We were asked, what is the length of segment QR? Okay, we were given a triangle, and the first thing I saw is that QS is the perpendicular bisector of segment PR. So I know that my two legs are congruent because point Q here is equidistant from the endpoints. So I can say that the length of PQ equals the length of RQ. I substitute in and I get N equals 3. And then I just plug it back in and my two side lengths are 8 units long each, which should not be a surprise. Now, how do we use this in the real world? Well, this is a good one. This is a really nice idea. This is a good, useful geometry idea. We have a amusement park here. We've got our paddle boats and our rolling coaster and our spaceship chute and our merry-go-round. And we know that our two most popular rides are the rolling coaster and the spaceship chute. And we want to put a t-shirt stand directly in the middle of those two, so that when people walk around, they'll go buy a t-shirt. Well, how are we going to do that? Well, I have a segment that connects my rolling coaster and my spaceship chute. And I am going to draw the perpendicular bisector, perpendicular, and it bisects that segment between the rolling coaster and the spaceship chute. And I know that any point on this perpendicular bisector is going to be equidistant from my two rides here. So it'll be equidistant from here and equidistant from here. So where do I want to put my t-shirt stand? I could put it right here in the middle, right? That's equidistant. Those two are congruent. I could put it up here so that when people get off the paddle boats and they're like all wet, this would still be equidistant to my two favorite rides. Perhaps we want it closer down here to the merry-go-round. It would still be equidistant from those two rides. Let's see, we should be marking these because we are good math people. We could put it a little closer here, and it would still be equidistant. So the point of this is if you have a segment and you draw the perpendicular bisector of that segment, any point that is on the perpendicular bisector, any point on line L here on the perpendicular bisector will be equidistant from your endpoints. And that's very useful. All right, that is fun with perpendicular bisectors. Now let's talk about the angle bisectors. First, we need a little bit of, I guess we could call it vocabulary, some prior knowledge. Distance from a point is the length of the perpendicular segment from the point to the line. So if I have line L here, and I want to find out how far away from line L point A is, I have to draw a line that is perpendicular. If I want to find out how far away from line L point B is, I have to draw a line that is perpendicular. So the key thing here is distance or length. We could call it distance. We might ought to call it distance. Distance is always measured perpendicular. Okay, it's an important idea that's going to follow us. So if we are now working with angles, we now have an angle here. And if we draw the angle bisector, this is ray, don't forget how to mark rays, ray AD. Remember, rays are named from the end point. Always has to be in the first position. So we draw our angle bisector, and we put a point, any point, on that angle bisector, and we measure the distance to the sides of the angle, right? And remember, distance is always measured perpendicular. Okay? Guess what's going to happen to those two lengths? You got it, they're going to be equal. So ray AD bisects our angle, and we measure the lengths of the perpendicular segments to the sides of the angle. These lengths are going to be equidistant. And that is going to be our angle bisector theorem. It says that a point on the angle bisector is going to be equidistant from the sides of the angle. So let's look at this here. We have our angle bisector. We choose any point on that, and we measure the distance to the sides. Now the requirement here is we have an angle bisector, and we measure the distance to the sides of the angle, and they are going to be the same. So we can say segment SP is congruent to segment SR. That's just definition of congruence again. Okay? So very similar, but notice we're putting a lot more lines in our diagrams here. You're going to have to be careful. You know that you are measuring length if you see the right angles, right? Because distance, you are measuring the distance if you see the right angles. And then, of course, we have the converse of the angle bisector theorem. So what was our requirement up here? If your point is on the angle bisector, and then the result was the point, this point right here, is equidistant from the sides of the angle. So what's our converse going to be? It says if you have a point, and the interior is kind of important, has to be inside the angle. If a point is equidistant from the sides of the angle, so we have a point and it is equidistant. How do we know that it's equidistant? Because it is being measured perpendicular and the segments are congruent, right? Segment SP is congruent to segment SR, so their lengths are the same. They are equidistant. That's just definition of congruence again. If the point is equidistant from the sides of the angle, then the point is on your angle bisector. So what you are able to do is to use your point and the vertex of the angle, and you can draw a line, 2 points. Well, you can draw a ray, you can draw a line. Ray is just part of a line, right? You can draw a ray that is the angle bisector. So ray QS bisects angle PQR. And what do we do with this? Well, we get a diagram like this. And we look and see what we have. I see right angles. I see an angle bisector. So I know I have an angle bisector that Ray NR is an angle bisector. And I know that any point on the angle bisector is equidistant. So because these are measured perpendicular, I can say they are equidistant. So if segment RM is congruent to segment RP, definition of congruence lets me say that they are equal, the lengths are equal, and that's our angle bisector theorem. I simply substitute in, solve for x is 5, substitute it back in, 7x, this length is 35. If we do segment RP is 2 times 5 plus 25, it's 10 plus 25, it's 35 as well. That should not be a surprise. We said they were congruent, which means they have equal lengths. This is the angle bisector theorem. The hardest part of these is seeing the information in the diagrams. So use your notes, match your pictures to your diagrams, and look for the important ideas here, right? Look for an angle bisector and a point on the angle bisector that has the right angles, right? That has the perpendicular lines going to the sides of the angle. Or back here on our perpendicular bisector theorem, look for a segment that has a perpendicular bisector of the segment. Don't forget, perpendicular bisector is two different things. So we have a perpendicular bisector of a segment and an angle bisector, and they have special properties. So as long as you are careful and look for your requirements, you will be just fine. So I hope you enjoy the homework.